Okay, hello everyone. For this video, I'm introducing a slightly different topic in the sense that it's a different realm of physics than we've been looked at previously. Previously, everything's been effectively incompressible. For this one, we're going to look at supersonic flow and take a look at what are some of the considerations with that, some of the basic physics selection, um, parameters, and things of that sort for a very, very basic supersonic problem and one that you can validate. So, the geometry of this isn't going to be anything I planned out in advance, but it will be a simple geometry that you can validate. So, we're going to need a few different parts here. So, we're going to start with a block. This is going to be a two-dimensional supersonic simulation. So it's going to start, I'm going to say 4 meters upstream. So we're going to call the start of our body as x equals 0. It's going to, the domain is going to start at y equals 0, which is going to be, again, in line with the bottom of our body, which is going to be a double wedge. Z equals 0, that's fine. It's going to go downstream really only to probably positive. No, we're going to terminate the ramp before the end of the domain. So we're going to go to, let's say, positive 10 meters. This might be a little bit long, but we'll figure it out. And it's also going to go 10 meters up. So let's go ahead and create a scene to show us what this block looks like. And now this is our domain, right? So let's create our actual body. So first off, we have a cone. This is going to start at x equals 0, and it's going to go to x equals 1 along the x-axis. So it starts at 0, 0, 0. It goes to 1, 0, 0. It has a start radius of 0. It's a sharp pointed cone. This might get a little bit complicated. Yeah, it'll be fine. And it's going to end with a radius. Oh boy. Now it's time for some math. So my calculator actually. Hold on just a second here. Okay. Just a little bit of trig to figure out that I believe if we want a 10 degree half angle cone, if it's 1 meter long, which it is, we want the height at the back to be 0.1763 blah 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 meters. So this will give us and actually we're going to extend this to 2 meters, and you'll see why in a second, but this is still going to be oh, it won't let me do math here. Sorry, 1 second. We're going to double this, and we're going to extend it to 2 meters, although we're only going to use the first meter of it. So this is still a 10 degree half angle cone. Okay, we're going to create. Now, starting at 1 meter and at our 0.35, no, at our original value, you'll see the type of geometry that I'm constructing in just a second here. 176. And we want this to be So this should be... Oh, that's actually only an additional... There we go. Let's try this again. 0.4663076. There we go. Create. Now, we got 76. Close. One more part, shape part block. This is going to start at x equals 2. 0 is fine. It's going to proceed to x equals 10. 0 0.64, 2, 6, 3, 4, 5. Create. Okay, let's see if I did this right. This could get a little bit tricky. So, we have our initial block, which is our domain. Actually, you know what? Let me name these. Good best practice is to name things as you make them. I'm just going to call it a trailing block for lack of a better term. We have a trailing cone, and we have a leading. Not the best naming scheme in the world. Actually, hold on, I think I got this backwards. Yeah, I got this backwards. Lead cone, trail cone. Okay. We are going to create a subtract operation, which is going to target all of these and is going to subtract everything else from our domain. So let's see if we can get what this looks like. So geometry scene, we're going to create a new geometry scene, and we are going to look at only our subtract. Let's see what this looks like. So this is what our domain is going to look like. Line view normal part. So it looks funky because we're cutting out a cone, but we have a 10-degree ramp and then a 25-degree ramp. So effectively, the flow is going to be turning 10 degrees, turning 15 degrees, and then it has a 25-degree relief angle, and it continues out of the domain. So it's effectively a ramped step, a double ramped step in supersonic flow. And this will be a two-dimensional simulation. So, for this block, we really don't have too many details that we care about, except we do care about our inlets. Obviously. Inlet. Bottom, top, etc. Let's see here. We have our simulation plane. And we have our outlet. We also have out of plane. And we're going to rerun the subtractor so it inherits all of those surfaces properly. Let's see here. So operation new Boolean. Bad for 2D meshing of our subtract. Execute that upon creation. New mesh, automated mesh 2D. Subtract a polygonal mesher, prism layer mesher. And we're going to need this to be pretty small. So we're going to start with 1 centimeter base size. We'll let it float down to 5% size. Number of prism layers is going to be Let's go with 6, but we want it to be a really thin prism layer, probably. Custom controls. The things we are going to care about are probably going to be things like our boundaries are going to have no prism layers. Prism layer disable. Also, they are probably going to want to be larger. So let's do custom. Target surface size is going to be something like 800%. We'll make the minimum 100 out on these boundaries. This is a far field refine. That is, we are refining the far field. New surface control. I don't really know how much we really need other controls per se. I'm going to not do a surface control. What I am going to do is a curve control. Let's see if we can figure out. Perfect. Okay, yeah, this will work quite well, I think. So if we pick... Okay, we don't want that, actually. So we probably don't want that. We also probably don't want that. Okay. Hmm. Ideally, I'd like to catch the intersection of these two as well, but that's going to be complicated. Let's see here. Let's actually just break these up. We're going to split all of these by angle. We'll have a whole bunch of curves, I'm well aware. It'll be a little bit of a pain in the ass to deal with. That is unfortunate, but workable. Those don't have that. Split by angle. Okay, let's see here. We're going to rerun the subtract, rerun that. Let's see what curves we have here. Probably not that one. This is why naming things helps, honestly. So let me just deselect basically all of these. Go ahead and leave that one. See if any of these curves do what I want. Not that one, not that one. Yeah, I don't think we can actually get it there. So we're going to do a slightly different thing. And we're going to place some cylinders to do volume refines. So let's do new cylinder. And these are going to be cylinders that don't look like they particularly align with this. That's okay. The important thing is that in the two-dimensional plane, they will occur at the right place. I'll make this 2 centimeters in diameter. So that's going to be one of them. Create. The other one is going to occur at the same. Let me see here. I'm looking at this in there we go. I need to look at this in parallel. And I could do the math and find out exactly where this is, which would be slightly more robust. But we can get this really, really, really freaking close by doing it this way. Create. And then I know this second one is going to occur at x equals 2 meters. At x equals 2 meters, so we can hit 2 meters. We can lock the x coordinate. And then we can get this to the exact height that it needs to be at. So right about there, and we can copy this field over here and hit create. So I'm going to call this refine. And actually, you can, if you have really complex geometry, what you can do is you can cheat a little bit, is because these will be alphabetical usually, is you can put a Z in front of it. So Z, refine, refine trailing corner, or at least in like regions level or anything else, they should show up in alphabetical order. But you could also find by searching. So let me see here. If you just type a number, I can just type refine. And it's going, going to find various things that match refine. Or it's at least going to find the first thing that matches refine. Let's see here. Okay, so we have 3 refines. I'm going to lose the curve control because that's what these cylinders take the place of. And we're going to place a volumetric refinement at our 3 cylinders. Bam, bam, bam. And let's see here. We are going to modify the 2D surface mesher. And this is going to be, I'm going to say 12.5%. So it's going to be a real small mesh right there. Now, we can get a little bit tricky here. So, I'm going to use what is known as a parameter. These are values that you can use in multiple places. Think about it as like a variable in programming. Instead of typing the same number out in a bazillion different places, you can define it once and just call it by name. So down here in Tools, there's a folder called Parameters. I'm going to create a new scalar parameter. I'm going to call initial shock angle. I'm going to create a second parameter, which I'm going to call secondary shock angle. And the reason is because if this is supersonic flow, we know that we're going to have a shock wave thrown off the front of this. We know we're going to have a shock wave thrown off this second shelf. What are those angles going to be? We should probably figure that out. But these are both going to be angles. So we can put in that they have the dimension of angle. So let's see here. And this will depend on Mach number, right? So we expect these to be oblique shocks. Let's see here. What I really need is to find an image of the theta beta Mach diagram. We can pull off some values here. So let's see here. For the first angle, we expect... hold on. Open image in new tab. This will do, I think. Okay, theta beta Mach diagram. Just ripped from the random corners of the internet. So for air, if we have an initial turning angle of 10 degrees, we expect our shock angle to be... Let's see here. How does this work? So this is a Mach 1 curve right here. I really wish these curves were better labeled. So as we go to higher Mach numbers, I really need this curve to be labeled. Sorry, 1 second here. Let me try and find a slightly better curve. That has these things labeled. Well, that has them labeled all right, but really, really hard to read. Yeah, I don't think that's actually... That's not actually Mach equals 1 for starters. There, we'll look at this one instead. It's a little bit hard to read, but is slightly more informative. So Mach 1 is, well, going to be the smallest one, I think. So the lowest curve is Mach infinity. So our deflection angle is 10 degrees, so it's more or less in the middle here. If we're going to go with, let's go with like Mach 2. Follow this line up. See here, Mach 2 is that curve. So we're looking right about here, which means we have a deflection angle of probably about 38 degrees. Now it gets a little bit complicated for the second one. I'm actually going to just kind of wing that one, but our initial shock angle is probably about 38 degrees, according to that. Assuming we do Mach 2 and this is a 10-degree angle. Our secondary Mach number is probably in the realm of like Mach 1.5-ish after it slows down through that oblique shock. And our turning angle is something more like 1 degree. Oh, that might actually give us a strong shock. We might need to crank up the Mach number a little bit. We'll see. But the secondary turning angle is probably like 50 degrees, give or take. 55 degrees. And the reason this is important is because we need to define some refinements here. So I'm going to create a surface control that is going to be specific to the leading edge shock refinement. And for this, we are going to look at oh, can I actually do that? That's interesting. Hold on, let me... Maybe I can't do that. Volumetric control, let's see here. Okay, we're going to do this a slightly different way. New shape part, cone. we're going to start it there, and we're going to extend it. We need to parameterize this cone. Hold on a second. So new shape part, cone. We're just going to create a semi-random cone, and we're going to see if we can tweak this. There we go. So the start location is 0, 0, whatever. 0, 0, 0. Actually, that's exactly right. The end angle, though, or the end coordinate, is going to be... I'm trying to remember how this theta beta Mach diagram works. It's been a while since I've done supersonic stuff. Theoretically, is going to be sine can I make a new parameter right here? Hold on. I'm going to make a new parameter called the shock refined length. And this is going to have dimensions of length, and it's going to be 5 meters long. Okay, let's try this again. Where did my cone go? Cone. Okay. Let's see if we can define this properly. So we're going to have, and notice we can select from our parameters right here. So we're going to have sine of our initial shock angle. I think it's just the initial shock angle. I might have this wrong, but we'll find out. Times our length. And then we're going to have for our y coordinate, our length times... Oh, I got this backwards. This is cosine. And this is sine. Because as the shock angle goes up, the y coordinate is going to get higher. Shock angle, and this is just going to be 0. So let's click OK, click OK, and start radius is going to be 1 centimeter. And if we want the shock spread angle, yeah, shock spread angle, we'll call this 2 degrees. This is going to default to 2 radians. 2 degrees. There we go. Let's see here. Cone. Now let's parameterize this some more. So we're going to say this is going to be 0.001, 0.01, excuse me, 1 centimeter plus the shock refined length times sine of the shock spread angle. Boom. So this is our shock wave refinement for our initial one, and you can tune this angle later. So if we wanted to change this initial shock angle, we can say, okay, right now this is floating up right there. Kind of get a good mental image of that. Let's just do something ridiculous and say the initial shock angle is 90 degrees. Oh, boom, 90 degrees. So we can just tweak this entire thing because we set up this definition. The refine initial shock volume. Okay, and I'm actually going to copy this and paste it. And we're going to edit it so I don't have to completely redefine it. So we're going to do a couple things here. We need to change its start coordinate. This is going to start at... Oh god, I don't even remember. I know it's x equals 1, right? I want to say this was like 0.167. Let's actually check. 0.175678. Right here. Okay, so that's going to start right there. We actually might want to start it just a little bit forward. 0.995. Negative 0.005. Just though it actually captures that very beginning corner right there. And we need to edit the shock angle that it's using. Or we need to actually augment it. So the shock refined length is fine. This needs to be, instead of the initial shock angle, this needs to be the secondary shock angle. And this needs to be plus 10 degrees. I don't know how much it's going to like units in the middle of this. We're going to find out. Degrees. Did it take that? It does not like that. Okay. We can also just do 10 degrees in radians is 0.17453. Plus 0.17453 radians. And this is because this is already traveling up at a 10-degree angle, right? The flow is going to become parallel to this first ramp, but our coordinate system hasn't changed. We also need to offset this by the starting coordinates. So 0.995 plus, and this is 0.175678, blah, 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 plus that. Okay, boom. So there's our shock angle. So we have our two shock volumes. You can see they actually intersect, right? And then we could also put a cone. Doesn't need to be nearly as pronounced, but we're also going to put a cone for a refinement that's going to start at, it's going to start at 2. So this is going to be for the expansion fan. We're going to lock this to 2 meters. Right about there-ish. And actually unlock this and make it slightly upstream. 1.99 aught, or 1.9, yeah, 1.98. 0.98. Actually, this isn't going to be the end. So it's going to go, let's say, 2 meters downstream. So it's going to go to 4 meters. It's going to stay at that same height. It's going to stay in plane. It's going to start with a 1 centimeter diameter. And it's end with a. I'm a little bit fuzzy on how expansion fans work, so I'm going to make this a little bit overkill. What I think is probably overkill. Okay, so we're going to have two volume controls: shock refine and expansion refine. Custom controls, new volume control. And theoretically, I don't think that expansion fan should require changing regardless of what we do to the Mach number. But the shock refines should not automatically adjust, but you can update the shock angle for both shocks, and it should adjust the cones dynamically with the way this has been set up. So, shock refine, we're going to take our secondary shock and our initial shock volumes and refine them. And we are going to keep this nice and small. We're going to try for, you know what, we're going to leave it at 10 and see how that works. We're going to plug this in. We're going to also attempt to refine this. And we're just going to say this is going to be like, this can be 25. And we'll see how much I've overcooked this mesh, or undercooked it, depending. So assign parts to regions, one region for each part, one region for each, or one boundary for each part surface, and let's see what this looks like. 20 foot. Oh boy. Yep, this one's going to take a minute. The fact that it's taking this long tells me that I might have overdone it. But we'll find out. Keep in mind, what I say takes a long time for this particular machine is going to be different from what takes a long time or what is taking longer than it should for you. Because if you're using less cores, slower cores, faster cores, more cores, what have you, the relative speed is going to be different. Or in this case, it's all down to the core clock speed. It has nothing to do with the number of cores just yet. So, as a really quick aside, just to fill a little bit of time while this is wrapping up, surface meshing, which is what it's doing right now, only ever uses one core. It is a single threaded process. Volume meshing, which is it's not even going to do because this is a two-dimensional mesh. Volume meshing can use however many cores you have. But because this can only ever use one core, one logical computing thread, This is limited strictly to effectively the clock speed of the processor and the number of instructions it can execute per second. If it were doing a volume mesh, the more cores, the better. But for surface mesh, it's just how fast are the cores of the processor. There's advanced cases where if you're meshing multiple things, multiple surfaces at once, it's a bit beyond the scope of this class, but there is a thing called concurrent meshing, which will do multiple independent surface meshes in parallel because they're not interacting. It'll do one surface mesh while it's working on another one, while it's working on another one, up to however many cores you have. That can be a really efficient way to save time if you're meshing many different surfaces or many different surface meshes all at once. Or even just multiple surface meshes all at once. However, it's kind of a niche case where you're not going to run into it huge. Or actually, allow me to step that back a little bit. You would probably run into it reasonably frequently if you were using STAR-CCM Plus on a regular basis, but in most cases it would be a fairly marginal benefit. Where it would be a major benefit is in a fairly would be for a fairly unique problem set. Where I've run into it fairly regularly was when needing to model not just the air around a surface, but also model the solid body itself for thermal properties. And if you have a whole bunch of solid bodies, you need to run a surface mesh on all of them before you run a volume mesh on all of them. So it can be highly beneficial to run that surface mesh in parallel. In concurrent mode, and then run the volume mesh in parallel to help save some time. Yeah, I'm starting to think I overdid this a little bit. By a little bit, I mean a lot, because you can see that it's using about 5 gigabytes of memory. This is probably on the complex side for what I'm going to ask you to do. Well, not necessarily on the complex side, but this mesh is probably finer. Okay, this mesh is done. Let's see how bad it is. Oh, that's taking a second just to load. Okay, we did forget one thing. And I do think this is definitely overcooked. Significantly. So I'm going to do two things here. The big problem I see is that I didn't give the domain a refinement. So the domain is just kind of growing to ridiculously large size. And the second thing is our base size is probably a bit small, honestly. Like, I like the cell size out here, but I don't like the cell size in here, and the cell size is too small in here. So what I'm going to do is I'm going to create a refinement for our domain to kind of put a cap of, yeah, we'll go with 400. Far field refine. I'm going to have those numbers 400%. And we're going to double the base size to 2 centimeters. We're going to run this again. Hopefully it's not going to take nearly as long. Last time it took Ooh boy, it took, what is that, 7 minutes? Ugh. It's going to be far faster this time with a double base size. But these cells are way the hell too small. Look at this. And honestly, I probably should have changed what was going on. So I'm not going to go through the entire top to bottom because this video is already sneaking up on 45 minutes. But we do want to set up a couple other important things. We want to set up boundary conditions. We want to set up our physics, and we want to at least try and run this a little bit to see what it looks like, if it runs, etc. I'm not going to bother with the reports or too many detailed scenes, but we're going to try and step through the rest of this pretty quickly after we have what looks like an acceptable mesh, and we'll see. We'll see if we got the shock angle right or not. I'm not sure if I did or not. Yeah, but by and large, this is a pretty good prism layer transition, like on average. Like in places, it's way coarse. Um, like honestly, that could probably come down another factor of two, and it would still be fine. But we'll leave well enough alone for the moment and see what it looks like. So we have a mesh. Next step is let's go select some physics conditions. This is going to be a steady simulation. It's going to be a supersonic air simulation. We're going to select coupled flow because it's supersonic. It's a high energy flow. We're going to select ideal gas because we do expect density to be changing. Could very well be turbulent. We're going to go with K omega turbulence model. We don't particularly need anything else here. We don't need gravity. Yeah, we don't need anything else. The big thing is it's coupled energy, it's ideal gas, steady supersonic flow. Close. So this we're going to name it as air. The subtract, we want to set some boundary conditions. The bottom is going to be we're going to call this a symmetry plane. So it's going to act like it's a wedge, right? It's going to act like the flow is the exact same on the top and bottom of that line. The inlet is going to be free stream. We are going to set this, the flow direction is in positive x, yes. The Mach number, we are going to set it as, not 21, that is a little bit ridiculous. We're going to set it as Mach 2. 300 Kelvin, sure, that's reasonable enough. Pressure outlet on the back. We're going to also have a pressure outlet on the top. These are all walls. That is fine. So effectively, we're looking at like the leading edge of like shock tube or some sharp edge thing with some sharp edge ramp. Let's see here. Save. Double wedge. I'm just gonna drop it on the desktop for the moment. Let's see here. Let's look at scenes, new scene, scalar. Let's look at Mach number in the lab reference frame. Yeah, this is going to run far slower, probably, than the simulation you're used to. We didn't really initialize the simulation. Uh, We might decide to crash on this here. I don't like what this is doing over here. Yeah, it's thinking about it. Okay, so a couple things here. It looks like, just from kind of a gut check, surface level inspection, let me add a new mesh displayer. Or why not? It looks like that we got that initial shock angle pretty close. It's a little bit off. Notice how this shock, it absolutely starts here. It's almost exactly in our cone, but it walks out a little bit. And this shock angle is like way low, actually. It needed to be higher than that. So let's go ahead and tweak the initial shock angle. We're going to tweak this up to 40 degrees. Let's see here. We'll even tweak it up to like 41 degrees. How about that? Boom. So that puts the shock nicely in the middle of that. And this shock angle we want to point way the heck up, actually. Secondary shock angle is like 70. Yeah, I don't particularly like that very much. But we can see kind of the expansion fan effects over here. And honestly, I should probably shuffle this cone forward a little bit. So if we look at this expansion fan, let's move this entire thing forward. By about that much. We can remesh. Yeah, but see, in this space, we're going from. Well, that really looks like kind of actually. Well, actually, this agrees pretty much exactly with what we'd expect, because I was expecting this to be a weak oblique shock, an attached weak oblique shock, with it drops the Mach number to about 1.5, from 2 to 1.5. And this is actually in the realm where this would be expected to be a strong shock. So this is a little bit of a complex thing. We could back off this ramp angle a little bit. Could do a couple things, but yeah, this definitely appears to be in an attached strong shock wave. And we're getting some interesting shock interactions. Like this is like you're seeing part of a weak shock and a strong shock, or you're seeing a weak shock appear after the strong shock is dissipating. If that makes sense. So let's try this again. And really what we would probably want to have actually is, if looking at this, we want to refine this a little bit further. Because we're getting shock-shock interactions, which is actually bending our shock wave. Normally shock waves are going to be straight, right? But this shock-shock interaction is actually having the effect of changing the shock angle and leaning it backwards. So really we'd want to have this little line, and then we'd want to have it continue up this way. And that would be a much better representation of what's going on here than what we've got. But this is a basic supersonic simulation, and you can sanity check these shock angles. As a matter of fact, we did base this initial shock angle off of a theta beta Mach diagram, and it was pretty gosh darn close. Like, we were off by like maybe a couple degrees, but that could be eyeball reading of a graph for starters. So that was pretty darn spot on. And there's some other changes we can make, but by and large, these changes are due to the fact that we have shock-shock interactions and other weird effects going on here. So let me go ahead and hide this really fast. Stop that. Let me turn off the mesh. Boom. So this is what our flow field looks like. Let's actually do one last thing for a very brief visualization. We're going to turn this into a line integral convolution velocity graph. We can see what the flow field looks like. So we have a sharp 10-degree turn, and then we can see as it approaches this shock wave, it does another like 15-degree turn-ish, but it's not quite direct. It's not quite straight. And then it also turns as an expansion fan around this corner and extends downstream. And this effect does walk off the top here. That's fine. That's more or less expected. The fact that this interacts with the boundary up here is fine because it's supersonic flow, and this is only going to have effects propagate downstream, not upstream. So this interaction has no bearing on what's happening down here. None. But the big thing is we have some pronounced shock-shock interaction over here. We have very definitive shock waves. And this is a basic 2D supersonic simulation. So we will have an assignment that is similar to this in the near future. It will be something that you can validate with basic shock angle, Mach number predictions, with basic supersonic flow math, which is actually very simple compared to subsonic flow math. You should be able to validate your supersonic simulation and make sure it's doing what you expect, at least pretty closely. Like, there will be some differences due to, again, relatively complex phenomena like shock-shock interactions will cause things. And you can kind of get stack up of effects that will cause things to not be quite like you expected, especially if you get strong detached shock waves, which is something that is going to attempt to be avoided in assignment 2 here. But you can validate this against basic hand calculations for supersonic flow. So I'm going to leave it there. This has been a little bit over an hour, and I'll post these up, and you guys can take a look at them and review at your leisure.